Optic Refraction by Michael Salcedo, David Guzman, Savelli Yepes, Mario Contreras, and Alder Fernandez.
Optics is a branch of physics that studies the behavior and properties of light, such as reflections, and the main topic of our demonstration, which is refractions. Simply, refraction is when light passes through two medias and the direction of light changes. The famous Pink Floyd album uses the idea of refraction on their album cover, with light entering the left side of the prism. Once it has entered, the speed of light slows down, bends, and changes direction. The light then refracts more, exiting the prism. Longer wavelengths tend to refract less, while shorter wavelengths tend to refract more. The angle of refraction orders the wavelengths displaying visible light spectrum and a rainbow exiting the right side. The same idea applies to rainbows that appear from rain. The white light from the sun enters the droplet, dispersion happens, the light then gets refracted, exiting the droplet, and the rainbow colors exit. Snell's law is used to calculate the degree of refraction and in relation to the incident ray.
Okay, this is the analysis of our experiment. So we successfully recreated the rainbow. This means that refraction did indeed take place. And obviously, from what we researched, of course, it means that the sun rays went from one medium to another, which was the air to the water droplets. They'd slow down and they would exit from different angles than what they would originally enter from. The order of the rainbow also shows us something that we researched, which of course is wavelength. The longer the wavelength, the harder it is for that ray to refract, which can be seen with red, as it's on top, so it's refracting less. And towards the bottom, we can see purple and yellow, also blue, which have shorter wavelengths. This allows them to quote unquote bend more than red, which of course is just refracting. With both of these together, it's obvious that we successfully replicated refraction in our own backyard. This is our system. It's simply a mirror and a bowl. And I put a piece of paper in the background so we can record where the lights go. These are our tools. On the far left, it's our green laser. The small one is our red one. And these other two photos are just to clarify that the green laser is from a flashlight, but the laser itself is at the bottom. This is to clarify regarding the source of the light. So these are our trials with the green laser. You can see the laser obviously on the mirror itself and on the piece of paper in the background. Same thing with the red one. For the red one, I actually got these zoomed in photos just because it was harder to see, and it might be harder to see on other screens, but you can see it on the mirror and also on the piece of paper. So these are our results and also some diagrams. As you can see, the red light appeared above the green light after being reflected by the mirror. So what we could see is that the red ray, or the red laser, got shot into the water. That's the incident ray. It got refracted downwards into the mirror, went back up, refracted again, and hit the paper. Same thing happened with the green laser. You can see the incident ray hits the other medium, refraction, hits the mirror, gets reflected upward, again refraction, and it comes out, this time at the bottom. This is simply supposed to be both of them. The black arrow is supposed to be both of the green and red lasers being shot at the same angle. Once they enter the water, the refraction happens and they are sent at different angles towards the mirror, as you can see. So because they hit the mirror at different angles, of course they're going to get reflected differently. Once they get reflected upwards, they again refract and exit at the exact same angle that they entered, but obviously at different positions. This is due to the wavelength. the wavelengths can affect how much refraction can affect them, which again goes into our results of the red laser appearing above the green one.